You don't have to be in the IT career field for long to realize that there is a lot of finger pointing going on in this game. It's always an IT person's job, it feels like, to be able to point the finger somewhere else that it's not their responsibility. For example, someone says, hey, the internet's slow. And you want to be able to say, well, it's a fill in your service provider there. It's the internet service provider. They must be, let me call them. They must be like it feels good for an IT person. It shouldn't be this way, but it is. It feels good for an IT person to be able to turn and say, it's not my fault, it's them. And let me prepare you as you are getting into this network world. You will find that finger pointed at you so often for issues that, well, it may be your fault. It may be our fault as network people. But for the most part, if we do our jobs well, it's not. It's an easy finger to point when somebody's like, hey, you know what? Things are just running slow. All the Microsoft team looks over and goes, Cisco guys, that's their issue. It must be them. Let's forward that ticket over to them. It's a slow thing. So if things feel slow, it must be a network thing. Or programmers. A lot of times, there might be a bug in their code. It's not always. Here I am pointing the finger right back. I'm like, it's their fault, and it's never our fault, right? So programmers a lot of times will have a bug in their code or whatever, and they'll be like, oh, it's the network. And the network guys are like, no, it's not. Everything works fine except for your program. I mean, it's your program. So you get this big finger pointing game. That's what I'm about to train you how to do. So this nugget that you're looking at right now is actually an afterthought. I was going through and putting together the flow, and I was like, okay, we got the base configuration, and I was about to get into VLANs, which is an ultra cool topic. I mean, kind of an earth-shattering topic in terms of network technology. And I'm sitting here thinking, I'm like, there's more. I felt like there's just more somewhere in between the base configuration, which we just talked about. We have our switches manageable, securely, all that kind of stuff. And then VLANs, which is over here. There's like this squishy middle ground, and that's where this nugget came from. Day-to-day operation of Cisco switches. Questions like, hey, the network is slow. What could cause that? Or let me give you kind of a more a bigger picture to that. What can you say or what can you do to prove that it's not the network or to prove that it is? One of those two. And that'll be some of the key interface counters. And then another one will be, the firewall admin contacts you and says, hey, there's somebody with this IP address that is just flooding our internet connection. They're causing tons of traffic. So they're like, where is that person? How do you find them? Finding devices using the MAC address table. So if somebody is pointing the finger at you saying you're the problem, your network is the issue, the best place to go is directly into the live switch interface. And that's where I want to keep it. Let's start off with the network is slow. That is one of the worst complaints that you can get. Not worst as in it's a major problem, although it could be. It's just like, what does that mean? I mean, it's like saying somebody coming up and be like, my car is broken. And you're like, well, what's wrong with your car? I don't know. And you're like, so what's broken about it? Like, I don't know. It just kind of doesn't run right. Well, so you see what I mean? It's kind of like the network slow. What does that mean? Like slow compared to home? Are you surfing the net and you can't watch your YouTube videos? I mean, what does that mean when you say the network is slow? Because it's one of the most painful things to really even quantify to say, here's what it means. So the biggest thing that we want to look at when we get network is slow is our interface counters. And as they relate to speed and duplex. Let me tell you the tale of speed and duplex. Speed and duplex has long since been an issue. When you connect a device, that's a mutant computer there, to a switch, both sides are set to auto. And now I'm drawing a computer, but I'm talking routers, servers, printers, everything can fall victim to this auto detect. And what do I mean by auto? That means that the network card is designed to auto detect the speed and duplex to figure out what the other side is. Are you 10 megabits per second? Are you 100? Are you gigabit per second? Are you full duplex to where you can send and receive at the same time? You can kind of do this at the same time. Or are you half duplex to where I can send and you receive and then I have to wait and you send and I receive? What are are you? So auto detect is supposed to resolve that, but there was problems. There was problems with auto detect in the 10 megabit per second world. There was problems with the auto detect mechanism in the 100 megabit per second world. They fixed the problems with auto detect when we got to gigabit per second, meaning it now works, and all the recommendations will say you should set both sides to auto ... if you're running gigabit speed. If you've got gigabit network cards everywhere, then great, but not everybody will have that, and not everybody will have that for quite some time, because it takes time for things like gigabit speed to trickle into all the devices. We've got a lot of, I know gigabit has been out for quite some time now, but only now are we seeing all the computers that are mass produced reflecting that. The IP phones, you think about phones. And phones affect that. They plug into the switch and then they connect to a device. Well, if you purchased 150 phones and they're all 100 megabits per second, then upgrading your network to gigabit just became that much more complex, because you don't just upgrade the switches and the computers anymore. Now you got to swap out all your phones. That's a major expense to justify if you look at what people use on average. On average, still today, people use maybe 8 megabits per second. 8, maybe less, I would say, of speed. I'm referencing a study I saw some time ago, but that's mostly surfing the web. That's people that are streaming. Just on average, and I'm not talking like average throughout the day. Average throughout the day would probably be like half a megabit per second. I'm talking like what's the peak that normal people use, and that's about what it is. So, with that being said, gigabit is a long ways off, and so we've got this auto deal to worry about. Most of the time, auto detect works okay, but when it doesn't, it can cause some major issues. The speed, I will say, always detects correctly. So if this side is 100 megabits per second and this side is 100 megabits per second, then they will always negotiate that. That component works fine. It's the duplex where the issue happens. One side detects, oh, this is a full duplex connection. The other side detects, oh, no, this is half duplex. Could be the computer, could be the switch. One side misdetects. So one side thinks it can send and receive at a time. The other side thinks it can only send or receive at a time, and what we end up with is collisions. So collisions are when this side is sending and this guy's like, whoa, I can't receive because I'm sending too. I'm just going to start dropping packets because they've collided. It's how the networks of old used to work when we had hubs everywhere. But now that we've moved into a switch generation, we should never see any collisions on the port. What's the result of getting collisions? Slow. Meaning, it's not like the link just goes down, although it may, depending on how many errors you get on the line. But it usually doesn't just go down. What happens is you start dropping a bunch of traffic because it's getting collisions. It's saying, oh, well, you sent, and I'm not supposed to be able to receive that at the same time I'm sending, so I'm drop. Now, traffic, if it uses TCP, which most applications does, will recover from that. It's like, oh, I got dropped. Let me slow down a little bit and resend. So the result is that we have people that are just like, it just doesn't feel as fast as it should be. Most of the time, it's a speed and duplex mismatch. So what does that mean? What do we do about that? Well, if we have troubled devices, now I would say usually it doesn't happen with the computers. It might be a router. That would be a major trouble device, or a server, or I don't know, maybe an IP phone or something. The things that would be major trouble devices are those kind of devices. Although computers can be. You can run into computers that misdetect the duplex. So what we have to do is hard code it. Not hard code it on one side, but on both sides of the connection. Because here's another trouble. With 100 megabits per second, the way the standard is written, the auto detect standard, is if one side is hard coded. Let's say I go to this computer and I say, okay, I'm turning off auto, no auto detect for you, and I'm putting you at 100 megabit per second full duplex, full dupe. And I connect this to a switch and I leave this guy as auto. So one guy is hard-coded, one guy is auto. What's the result? Well, the way that the standard is written, the auto-detect standard, is if this guy can't detect what the other side is, and he won't be able to because we've turned off auto negotiation on this side. If he can't detect what the other side is, he's going to resort to 100 megabit per second half. What? What? Thelma, did he say half? Half duplex every single time. Because you have to remember, 100 megabits per second, that standard was created when it was an era where half duplex devices were the norm. They were very common out there. And what they said when they created the auto detect standard is they said, you know what? If you can't figure it out, it's safer to default to half than it is to default to full duplex. Well, nowadays, they fixed that with gigabit per second. When gigabit came out, everybody's like, well, good grief, who uses half duplex anymore? Let's make the default full duplex, which is why the auto detect issues really kind of started fading away as gigabit per second came out. So the key is, if we have devices, and let me say this. I'm trying to think of a way to put this into a good rule of thumb to follow. If you have 100 megabit per second devices, so hang on, let me do this. Clear all this up. If we have 100 megabit per second devices, and they are key devices, hard code them. What's a key device? You tell me. What is a key device? Think about it in your head. What is it? It is a server. It is a router that a lot of people use. It is maybe a surveillance camera for the security system. Or, I mean, you have to think about your environment and think, if XYZ went down, that would cause some major issues. Those are key devices. Those are the ones you want to hard code. So let's just say we've got a surveillance camera that watches the lobby all hours of the day and night, or something. That's a key device where I would go into the camera itself, probably a web GUI that would be mounted for that guy. And I would say this is 100 megabit per second full duplex. Then I'd go into the switch port and say, this is 100 megabits per second full duplex. Hard code any key device if it's in the 100 megabit per second era. If it's gigabit, use auto. Keep auto detect turned on, because that usually solves everything, and it's just a lot less work if you do that. So, okay, we've got that. We've got the rules. Now, what about end computers? Should we go to every single computer in our network and hard code the computer to be 100? I mean, if we're using 100 and hard code the port, I would say no, because computers aren't key devices. Is there a chance that one of them could misdetect if both sides are set to auto? Yes, absolutely, the chance is there. But I would say the success rate on computers is, this is a gut feeling, it's probably 98% success on detecting. So that 2 to 5% that do misdetect, and this varies, different network cards work differently, but on those 2 to 5% that misdetect, it's much easier to go troubleshoot those individually than hard code everything in your entire enterprise. So here's how you do it. On the Cisco side, which is the side you'll want to know, you go to the interface that you are concerned about. Let's say, and I should also mention, let's just say this interface right here. Let me also mention. Let's do this one. That this is not something, if it's a key device, that you would want to do during production hours unless it's causing a major issue and everybody's approved it. Because the port will go down when you do this. So essentially network connectivity lost, and it will come back up. It's usually maybe a 5 to 10 second outage. And you're like, well, 5 seconds, 10 seconds, what's the big deal there? Well, depending on the kind of device that it is, it's a key server. People are transferring files, maybe streaming files off of that, or a router connection where voice over IP. I mean, 5 seconds of audio cutting out on voice over IP is death. Nobody has the patience to wait. They'll go, hello, hello, click. We live in a high-speed society. So the way that you do this is go under the interface that you want to hard code, and the command is speed, and you type in what the speed is. Speed 100. It's now hard coded. Duplex. And by the way, if you hard code one, you have to hard code both. So I'm going to do duplex full. So I'm going to put that in there. thought just crossed my mind. You see what's happening. Our interface is going up and down every single time I do this. So that you can think of that as a mini outage. But now that port is hard coded. Now I would go to the other side. Let's say fast Ethernet 0/16 connected to my computer. That's where I would bust out the control panel, and let's see. I've got to navigate around in here. So let's view the status. Okay, change adapter settings on my network. There we go. So let's just say LAN 2. Go to the property. You got to dig for this. This is why you don't want to do it on each one of the devices. So you kind of go to the adapter properties. Let's see, advanced. We've got connection type. There we go. Connection type. It's kind of different depending on the driver for the network card. But this is where I can come in and say, okay, it's set to auto right now, but I could also go 100 full or 100 half, and that's how I would hard code the other side to match that. Now, there is another feature that has come out. It's called Auto MDIX. Essentially, this feature, it's really cool, allows the switch to determine what ports are being used, or let me clarify that. Determine what pins of the network cable are being used for transmit or receive. See, there's always been this deal, and we mentioned it earlier in this series, to where we say, okay, well, if you're connecting a computer to a switch, we have to use a straight through cable. If that's totally spelled wrong. You get it though. Straight through cable, right? To connect dissimilar devices. Now, if we connect similar devices, like I connect this switch to this switch and this switch to this switch, that's where we use a crossover cable. And I would say that's still a good standard to follow. But since Auto MDIX came out, which is probably about 5-6 years ago, I'm in 2013 right now, so 5-6 years ago that this standard was released, it now can detect. You can use a crossover cable to connect a computer. I can use a straight through cable to connect switches together because it will detect it, but Auto MDIX relies on auto negotiation. So if I go into a port and type in speed auto duplex auto, or wait a sec, speed 100 duplex full, just what I did right now, then Auto MDIX won't be able to detect the other side anymore. So we have to use the right cables. We can't just use a crossover cable to connect a PC anymore because it's not going to be able to detect which pins are being used. It's all kind of wrapped together into that big auto detect mechanism. Second piece, the network is slow. We can go in and hard code the speed in duplex, but how do you know if you have to? How do you know if if there really are errors on the line? Well, that's because, shrinking. That's because I can go into the interfaces and check the counters. So I connected a few more cables just for this. I brought up fast Ethernet 016, 018. So I can go in and do let's drop back out, show interface, not show IP interface in this case, show interface, and I want to zoom in on fast Ethernet 0/18. Okay. First thing I want to look at, if somebody's saying the network's slow, I'm going to come in there and say, well, what are you set to? In this case, I can see they are set to full duplex, 100 megabits per second. Matter of fact, let me couple one thing in here. I'm going to do a show run interface fast Ethernet 0/18, which shows me the configuration. There's pretty much nothing underneath that interface right now. So I can look and I can go, okay, you are currently set to full duplex, 100 megabits per second. That makes me feel good. So if they're complaining about slowness, then I'm going to start coming down here and saying, okay, well, hang on, I cut off that output. Let me look down at your packet statistics. Now I can see this is actually my computer right now. I've got traffic always going to it. I can see, this is key right here. Full duplex, 100 megabits per second. This is key right here. I see the interface is up. Line protocol is up. That means it's physically connected. That's the first up. And then line protocol is up. That means it's communicating. I drop down. I go, okay, well, we've got queues. If you're getting into routers and things like that, you would check your queues because this tells you if packets are really bottling up, like there's not enough bandwidth to send them. But for now, on a switch, you usually don't worry about that. But this gives me a lot of good feel. So I go, okay, right now, input rate. Now, so input, what does that mean? It means put yourself in the role of the switch. You are a switch. Ding, designated. I'm receiving, somebody's putting into me as a switch 142,000 bits per second. So that tells me 142 kilobits per second in terms of network speed. And on an output rate, meaning leaving me being a switch, as in going out fast Ethernet 0/18 to whatever device that is, I'm sending, looks like a million, 408,000 bits per second, which is about 1.4 megabits per second, if I'm looking in terms of bandwidth. I go, okay, well, that gives me a feel over the last 5 minutes of how that's been. And then it goes into some totals. It says, okay, total, we've had this many packets input. I've seen this many broadcasts. And I'm like, okay, that's good. That's good. Okay, packets output, that's good. That's good. Here's what I'm looking for. Right there. Collision and late collision. Collision means there was a normal collision on the line. Now, if we're in a switch world, never should you see that. Ever. Period. Done. End of story. In a switch environment, there should never be a collision, because full duplex means both sides, as long as to their heart's content, they can send at 100 megabits per second and receive at 100 megabits per second at the same time. We won't have a collision. Collision shouldn't happen. Now, let me do this. I actually beforehand kind of messed around, and I tweaked my fast Ethernet 0/16 interface. Now I fixed it at this point. All I did was hard code it to half duplex, 100 megabits per second. Did some file transfers because I wanted to show you these. It is showing up now. If you always got to put these in perspective. You have to go, okay, total I had 352,000. Of that, 6,000 were collisions. That would be, well, I would say even seeing like 10 or 12, the key is this continuing to happen? Hit the up arrow a couple times. Take a look. Do I continue to see this counter moving up? Because if I do, it's still a problem. If not, then it should be okay. Now, I caused this. I actually went in and hard-coded it to be half duplex, but that's something that immediately will signal us to where, okay, something is colliding on the other side. Now you might be saying, okay, what's up? You got collisions, and then you got late collisions. What's up with that? Difference between those two is really, when did the collision happen? See, there's normal collisions, and then there's late collisions. Don't you love when you make those brilliant statements and you're like, yeah, that was really what we just saw there, right? So normal collision, what's the difference? Normal collisions is in the hub world. If this was a hub, you've got all the different devices that are listening, right? They're all listening to see if they can send, because only one person can send at a time. So this guy, he's kind of got this big old ear. He's listening to the cable to try and hear if anybody's talking. Well, this guy's got a big old ear. He's listening too. And the way that the timers work is if there is a collision that's going to happen, it's always going to be within the first 32 bytes of the frame. So as this guy is starting to send, a normal collision will always happen within the first 32 bytes. Just the way that they engineered the timers of how they listen, how they send, that the collision will always happen there. A late collision means this guy got, he's sending, a 1,500 byte packet, which is as big as they can be on a normal Ethernet cable, and somewhere around byte 732. That he detected data coming in at the same time he was trying to send. That means that's beyond the normal Ethernet standard. If you're in a hub world, in normal collisions will happen all the time in a hub world, but it's always going to happen within the first 32 bytes. If you go beyond that, it's considered a late collision. Late collisions are always indicative of a duplex mismatch. It's like if you see those taken up, hands down, you've got a duplex mismatch. This could happen, for instance, if I plugged my switch into a hub, and I've got a bunch of devices on that hub that are all talking. Then I would expect to see a bunch of normal collisions, because hubs cause collision. But if it's a late collision, then it's definitely something is connected, and there is a duplex mismatch. Now, we know that's a lot of time just to talk about speed and duplex mismatches, but it really is a big issue. It happens commonly, and it also exposes you to the interface counters. So now you have a counter argument. If somebody's like, it's the network, and they point at you, you go, well, no, I'm looking here. Well, not a good example there. Well, yeah, it is the network if that's the case. But you can look at your statistics and be like, oh, no, I'm seeing packets sent, packets received. Now you got to keep in mind that you want to make sure you trace it end to to end. So, for instance, if they're saying, "Oh, well, the connections are slow," and you go, "Well, to what?" They go, "Well, from that host over there, Joe's computer over to our server. That's where it's slow." You gotta keep eyes right here and say, "Okay, well, looks like everything's good there," but also you gotta check this link and check this link. Make sure the whole way through where we don't have any of those collisions or duplex mismatches or anything like that, because Joe could just be one victim of a bigger issue that maybe Joe just happens to be the first one to report. So follow the path. Now, you also saw when we saw this, you're able to really get a lot of those key statistics and compare. Now looking at this, there's stuff. I mean, this output initially, if you're new to Cisco, can be overwhelming. It's like, well, what is a runt? What's a what? What's a babble? What does that mean? I mean, there's a lot under here where it's like, well, what is all of that? Now, some of them are common. What I just showed you. Knowing collisions, that's common. Knowing packets input and output. I mean, if somebody, I'll tell you frankly, if somebody walked up to me right now and they're like, "What's a babble?" I'd immediately think my 4-month-old kind of. He's like, I wouldn't know. I have to look at a reference book. But if somebody asked me what's a collision, I'd know the answer. What's a CRC error? That's a big one. CRC, cyclical redundancy check, is every single frame when you send it. It's the little piece at the very end of it. I think we talked about this early on in the Nugget, which makes sure it's a little hash. That is run on that packet before it's sent that says, okay, I run this all through a big algorithm, and if anything in this changes, by the time it gets from point A to point B, this CRC won't match, and it will be considered a bad packet. So if I see a whole bunch of CRC errors, I'm going to be like, oh, this may be a bad cable. Maybe this cable is going by some interference, like fluorescent lighting. I've got it wound around a fluorescent light, or something that's really causing our data to kind of get messed up between point A and point B. So some of these are going to be key counters. I would say that's probably between input, output, collisions, and all that. Those are the key ones. The other stuff, I mean, that's what reference books are made for. You won't be asked to quote what a babble is. So that kind of leads me into the last piece. Joe is reporting an issue, or someone is coming to you and saying, well, where is Joe in the network? Or we're having this IP address is causing a lot of issues. What I said when I started this whole nugget, where are they? Now, if you're in a big company, a lot of times they'll have monitoring software that kind of pull it all. You'll go to a web interface and say, where is this MAC address? And it's like, and kind of just spits it out, and you go, oh, okay, it's over there. But most people don't have those kind of tools at their disposal. Most people will start something like this. Like let's say they go, okay, well, that's 172.30.100.1. And maybe Joe is whatever IP address. Where are they on the network? The first thing that you're going to do is open a command prompt from a device that's on that same network. And I would say, okay, well, let's do a ping, 172.30.100.1. Oh, okay, I'm getting a reply. Good, because that tells me I can get to that IP address, which means I can do an ARP-A. What is this? This gives me the ARP table on my computer. Remember what ARP is? Address Resolution Protocol. When I ping this, my computer has to send a broadcast to find out what MAC address that IP address really has. And it's going to cache that in its ARP table. So I can do an ARP-A and hit the Enter key and see all of the MAC addresses that my computer knows about. And there it is. I go, okay, right there is 172.30.100.1. As well as 6, as well as 16, as well as 25. I see all of these IP addresses that at some point my computer learned about dynamically on the network and has added to its ARP table. So now I can go to my switch and I can say, okay, well, I want to see, give me a show of the MAC address table. And some versions of the iOS is MAC dash address table. Some is MAC space address. Just kind of use question mark to figure it out. And I can see right here, okay, I've got all these MAC addresses. Now keep in mind, in a large network, this is going to be pure overwhelming. I mean, you'll have 50 pages of MAC addresses that have been learned on this device. So a lot of times, using a little filter action is going to come in really handy. We're going to say, okay, well, I see the MAC address right here ends in 0101. And I know Cisco doesn't do dashes, they use periods. So I'll do include 0101. And now, look at that. Spits out right there exactly what I'm looking for. I'll go, okay, that MAC address is located on fast Ethernet 0/18. Now I know you're like, okay, well, wait a sec. So is that. It's the same one. So is that. I mean, what's up? Is this broken? How do I have all these MAC addresses on one port? I mean, I don't get it. Well, a lot of times if I've got a switch, this is my environment, I've got a switch with my computer plugged into it, and that is uplinked on fast Ethernet 0/18 to another switch. And that goes to another switch and another switch and so on and so forth. So as all the devices that are plugged in here and here and here communicate, well, they're all coming in this one interface. So from my switch's perspective, right here, it's learning, MAC address ABCD. It's learning all of them on that one interface, and that's fine. That's normal. But what that tells me is, if I'm on the search, if I'm like, okay, it looks like, I've got to go out. Let's say this is fast Ethernet 0/18. I've got to go out that port to find it, and I see a ton of MAC addresses on that port. That tells me that's another switch. So I have to telnet to that switch and find out what's going on over there. And we'll get into things later on like show CDP neighbors, which is actually not running right now. But that'll tell me what the next switch in line is, and I can actually telnet to that switch and do the same show command from there. But for instance, if I was trying to find my computer, I know my computer right here is 172.30.139. That's my IP address. Now, it's not going to show up in the ARP table because it's me. I don't have to figure out my MAC address. For me, I do an ipconfig /all, and I would come up here and say, well, let's say I've got there's my MAC address. I use the first 4 digits are sometimes shared, common between many different devices. The last 4 are usually unique, not always, but usually, to where my device will not have that same last 4 digits as another. So I can come here and do a show MAC address table and zoom in and say, show me 6C32. Immediately I go, okay, great. This guy is out fast Ethernet 0/16, and I can zoom in there and locate that device. Now comes the fun part of, okay, I know it's plugged in there. Now where's that go? And that's where a good documented physical network layout is good. And hopefully whatever company did your cabling allows you to be able to go, okay, well, let's run that. Okay, that connects to that, and that ends up going out to whatever port that's located on wall jack 9. So finding any device in your network can be done just through a series of ARP commands. Do a ARP-A on your PC. And by the way, even though it's Cisco, Cisco does expect you to know some of those commands from the PC, like ARP-A, like ipconfig, like ping, to where you can test the different devices that way. If you're on the switch, by the way, the switch can ARP as well. I can do a show ARP on the switch and find out what IP addresses it's resolved. Now you might say, well, that's odd. How come the switch only sees this one IP address in its ARP table, but we've got all of wouldn't you expect to see all of those in its ARP table? Well, remember the switch's perspective. The switch is located on the 10.1.1.10 network. So the only thing that it's going to be able to ARP for are things that are in that subnet. Now I just, to do this nugget, I plugged in a whole bunch of other devices. I uplinked this little lab switch to the rest of my network so I could get a bunch of MAC addresses showing up that are on, we'll call it Jeremy's production network, but the switch isn't on that network. It's layer 2, it may have those MAC addresses, but at layer 3, its IP address is not on the same network. So it's just all of that is going through the switch, not to the switch. So the ARP table of the switch is things that are going to the switch. Like, I want to communicate with you, CBT switch. All of these other things are just going, I don't care who you are, CBT switch. I'm going through you to reach whatever destination I'm trying to get to. So that's why we see the discrepancy there. So we have seen how we can kind of fight back if somebody says the network is slow. Speed and duplex, that's almost always where that issue is at, or could be bad cabling. Look for those CRC errors, things like that. We looked at the key interface counters and how to locate devices using a series of ARP and show MAC address table commands. I hope this has been informative for you, and I'd like to thank you for viewing.